Hello everybody, can you hear me?
Yes, sir.
Okay, welcome to online class on CSE 461 Algorithm Engineering. From the last class, we were studying a branch and reduce technique to solve independent set problem. I just quickly review the last class. In last class, mostly we have learned the basic idea of branch and reduce algorithm. And in this technique to solve the problem, what we do, we reduce the instances and we solve the reduced instances and we choose the best solutions of the reduced instances to make the solution of G. And we can remember that this technique is based on some observations, and these observations are if we consider V is a vertex in an independent set I, then we can observe that none of the neighbors can be in I. And again, if we consider the maximum independent set I, and we assume that V is not in that maximum independent set, then it is true that at least one of the neighbors of V is in this maximum independent set I. Why? Because if V is not in the maximum independent set, then I union of V would be a larger independent set, and which will be a contradiction to our assumption. Now we define NV. NV is the set of neighbors of V including V. That is, it is called the closed neighborhood of V. Then for every vertex V and every maximal independent set I, there is a vertex Y NV such that Y is in I. That if we consider a maximum independent set I, then at least one vertex from NV will be in I. And based on this observation, we propose a reduction rule. That is, we choose a minimum degree vertex from the neighborhood and for each vertex of its closed neighborhood, we consider a subproblem. And we assume that this vertex U belongs to this maximum independent set. And so we take G minus NU as a reduced subproblem. I just quickly review the idea using this graph. So this is a input graph, and in this graph, these vertices say E has degree 2, G has degree 2, and C has degree 2, and all other vertices have degree more than 2. So these vertices EC, EC, and G are minimum degree vertices. So among these vertices, we choose arbitrarily one vertex. Say we choose vertex G. Then we construct these reduced instances like this. From G, we delete the neighborhood of G. The neighborhood of G contains the vertex B, G, and D. So if we delete these three vertices, and you know that deletion of a vertex means that we delete the vertex, and also we delete the edges incident to that vertex. So we delete B, G, and D, and we get this instance. And if we delete the neighborhood of B, the neighborhood of B contains B, A, G, and C, and then we get this instance. And if we delete the neighborhood of D, and that is neighborhood of D contains D itself, G, C, G, A, F, and E, and only the vertex B is remained. So we get this instance. And continuing these techniques, that is here, the minimum degree vertex is vertex C, and if we delete this one, we get this instance. And here, the minimum degree vertex are A and E, and we can choose any one as V. So we choose A, so we delete a neighborhood of vertices A, and then we get vertex E. And if we delete the neighborhood of vertex B, since A and F are in the neighborhood of vertex A, so we delete F, so neighborhood of F, then all vertices will be deleted because A, E, and F are in the neighborhood of F. So we give a vertex with empty vertex set, a graph with empty vertex set. Note that in this construction of the tree, each leaf node will be a graph of empty vertex set. Now, from this tree, we can construct independent set. In fact, we can construct every independent set of a graph. From starting from a leaf node to a following the path to the root, you will get an independent set. For example, if you consider this rightmost leaf node, then you follow the path to the root. Here is the vertex B, and we have deleted vertex B, and here we have deleted vertex, the neighborhood vertex D. So B and D constitutes an independent set of this input graph. Do you understand?
Yes, sir.
So if you follow from the leaf node to the root node, then it is an independent set which contains the vertices D and B. If you consider any other independent set, so from this leaf node where we have deleted the neighborhood of vertices F, so here F and here B, so we get F and B is an independent set of this input graph. And similarly, you can find all independent set of this input graph using this tree. And if you want to find the maximum independent set, so you can compute in bottom-up fashion, and you get the maximum independent set of this graph. So from this here, say here we have deleted vertex E, that is leftmost leaf node, vertex E, and then vertex A. So EA is an independent set of this graph. And then here we have deleted C. So we have independent set A, E, A, and C is an independent set of this graph. And we have deleted G. So here we get an independent set of 4 vertices, which is E, A, C, and G. And if you consider that, if for each node, for this node, it has 2 children. So from these children, you get independent set EA, and from these children, you get independent set F. So you get an independent set of 2 vertex, and you get an independent set of 1 vertex. So which one is larger? The vertices with 2 independent set with 2 vertices is larger. So we take this one as a maximum independent set for this instance. And similarly, we get a maximum independent of these instances, and also construct the maximum independent set of these instances and these instances. And finally, among these 3 maximum independent sets, we pick or we choose the largest one, and we get the maximum independent set of this graph. Now, you can easily realize or observe that this algorithm or this process can be implemented using a recursive algorithm. Do you understand it? That this method can be implemented in a recursive fashion?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. Now, we see the algorithm. Here, the algorithm input is our graph, and output a maximum independent set S of G and the size K of the maximum independent set. And this is the leaf node condition. That is, if there is no vertex in the graph G, then the independent set of that instance is 0, null. Because there is no vertex. And also K is 0, and return. Return means we just break from this point. And let V be a vertex of minimum degree G, and let Sx be a minimum independent set in G minus Nx, and Kx is the cardinality of Sx. So recursively, we can find that for every x in NP2, we find among these the maximum one we pick. And here is the for every one we recursively call its set, and we choose the maximum one as, and vertex x we have deleted, so you take the union of sx and x, which is among the maximum of these values, which will be the independent set S, and k will be this one. So is it clear to you, the algorithm?
Yes, sir.
Is there any question until now?
No, sir.
Okay, now we are going to analyze the time complexity of this algorithm. And we can see that the above algorithm and we can analyze complexity by writing recurrence relation. Let V vertex of minimum degree in G with dv is the minimum, and let v1, v2, vdv be the neighbors of V in G. The closed neighborhood of N is V itself and its neighbors v1, v2 to vd, v subscript d of V. We can write the following recurrence relation for the time complexity of Tn for G of n vertices. Carefully follow the recurrence relation. This is Tn is less than equal to C. This is constant. I will explain this constant later. And this part is for the vertex V, and this part is for the vertex of neighbors of V. So I think the recurrence relation is clear to you.
স্যার এই স্লাইডটা কি আরেকবার রিপিট করা যাবে
কোনটা?
স্যার এই টাইম কমপ্লেক্সিটিটা?
আচ্ছা, এখানে আমরা কি করছি, we are considering the recursive algorithm, that is we have seen already recursive algorithm. So this is the time complexity or for finding maximum, the time for finding maximum independent set of a graph of n vertices. Tn of n vertices, this is the time of for finding maximum independent set of n vertices, which is I just explained this later. This part, that is T, that is recursively we call the instance where we delete the vertices, that is neighborhood of vertices of V. So with n minus dv minus 1, this is the number of vertices there for that part, and this part is for each of these children we get this one. And actually this part C, we feel this is a constant, but here we are using a different notation for time complexity, and which is that is polynomial of n also treated as a constant. This is order Stern notation. I have explained in some first class of related to exact algorithm. Can you remember it? It is O star order big O star. That means that this will be that is exponential function, and polynomial will be absorbed in the big O star notation.
Sir,
Yes.
sir, can you please explain this n minus degree of V minus 1? Where did this minus 1 come from?
Okay.
Sir, another question related to this one. Sir,
Okay.
we are doing a sum of the whole 1 to d of v. So why do you take a term out of it and write it like n minus dv minus 1?
Sorry, I could not understand your question.
So can we merge the second term with the third term of the
yes, we can, but this is okay, is a smaller term and this is larger term. We will finally merge these two, because this is the dv is the smallest one, because we choose the degree, smallest degree, and this is the dvi. Dvi is greater than dv.
Yes.
Okay, I just go through this deduction and then come back. Okay.
Okay, sir.
Sir.
So here,
Sir, I think since we are also excluding the vertex of minimum degree, uh,
yes.
I think the
So
-1 comes from that.
yes, exactly. So that is why, because the NV contains its neighbors and itself. So DV and itself. That is why it comes. You are right. Okay. Is it clear?
Yes, sir.
Now consider that since V is a vertex of minimum degree in G, the following relations holds because dV is less than equal to dVi. It is clear because since dV is minimum degree, and n minus dVi minus 1 is less than equal to n minus dV minus 1. So this is the smallest one. So this, if you negate these things, then it will be larger than this one for every vertex Vi I in this set. Is it clear?
Yes, sir.
Now, uh, since Tn is a monotone function, and hence relation is also hold. That is T of n dvi. This is the is less than this, since this part is smaller. So this time will be smaller. So this part is larger. Its time will be larger. So this relation will hold. Is it all clear? And we assume that t0 equal to 1, or we can assume t0 equal to c also. Okay. Now we get this one, tn equal to c plus tn of dpi. This relation we have seen. So this is c plus dv plus 1. So here we have merged this second and third term. We have merged this second and third term. So this term will be number of dv, and this is one term. So dv plus 1. dv plus 1 into tn minus dv minus 1, because we are taking the larger one here. So this relation is less than equal. Is it clear?
Sir, can you please repeat this part?
Okay. This tn, this relationship we have already seen in previous slides. So from
Yeah.
here, this is c, and this term is one term, and here there are dv term. And since dv is this term is say larger than this one, so all term can be replaced by this also can be replaced by this term.
Yes, sir.
So we get this term multiplies by this 1 to d and 1, that is dv. And uh, uh, actually there is a mistake in typing here. This v will be dv here.
Yes, sir.
Okay, so there is a mistake in typing here. So here this v is dv, not here. V is not here. So this term and this term will be this term. So this count is dv plus 1. So dv plus 1 times t of n minus dv minus 1. Is it clear?
Yes.
Clear it is?
Yes, sir.
Sir.
Is there any question until now?
No, sir.
Okay, now we assume that let take dv plus 1, this term, as s. So the relationship becomes tn is less than equal to c plus s into tn minus s. From here, s into tn minus s. And if we expand this, we'll get this term, and which is a progressive series, and you get this O star of s n minus s. Here O star we take because we consider that C absorbed any polynomial functions also.
Yes.
Is it clear?
Yes.
Everybody is okay?
Sir, I didn't get this summation, this series part. How did you
Yes.
expand this thing?
Actually, this is very, you just recursively expand this one. Recursively expand this one. I think you did this several times in many courses,
Oh,
especially in
okay.
2007. Okay. So you expand this term, and this is a progressive series, and by formula, you can use this part.
Okay, sir.
Is it clear?
Yes, sir. Yes, sir.
Okay. Now, uh, if we consider that is for s is greater than equal to 0, the function fs equal to s to the power 1 by s has its maximum value when s equal to e. Can you say, anybody, what is the value of e? What is the value of e? Do you know?
Sir, 2.71.
Hey, 2.7 something, and which is closer to into which integer?
3.
So 3.
3. So considering s as an integer, the maximum occurs when s equal to 3. And thus we obtain Tn equal to order big O star of 3 n to the power n by 3. So this gets the time complexity of this algorithm. And hence the running time of this algorithm is this part, and which is faster than the brute force algorithm time complexity, that is omega of 2 to the power n. And if you plot these two functions, then you will get that this is the maroon, that is purple color, is 2 to the power x, and this one is 2 to the power 3 to the power x by 3, which is drawn in green color. So this function is faster than this function. So we have obtained a faster algorithm using branch and reduce technique.
So it is still exponential, isn't it?
Still exponential. As I told you earlier, that we are studying the exact algorithms for hard problems, and it is very unlikely that we will get a polynomial time algorithm for hard problems. So all algorithms will be of, if we want to get an exponential time algorithm, an exact algorithm, of course its time complexity will be exponential. But our strategy is to get a better, faster algorithm so that we can use it for small value of our that is input size. Is it clear?
Yes, sir.
So today I will just this part, complete up to this part, and so if you have any question, you can ask me.
Sir, can you please repeat that recursive algorithm?
Okay. Here, so this part is that is base part,
Yes,
initialization,
sir.
that is this base part, that is we consider it as a leaf node, and if there is no vertex, then the independent set is empty, and also k is 0. So this is clear. And now for any other node, we considering these things. Let V be a vertex of minimum degree in G, and Sx be the minimum independent set in G minus Nx, and Kx is Sx. So if you check this one, so if there is any question, then I will explain.
No, sir, I think got it. I was having problem with this SX thing. Then I realized that we are propagating the maximum independence set from below and then attaching our nodes. So that is this SX and KX4.
Yeah, yes.
Yes, sir. Thank you, sir.